Question A is, which field is stronger, B1 or B2?
I'll say B2.
Just B1.
Which one's applying more force on it?
B1.
Which one's turning it faster?
Oh, that was B1.
B1. Then B, which direction of the field, what's the direction of the fields?
B1 is in, B2 is out.
Okay, let's go. Whoop, whoop. Yes, so this would be in, because it's an electron, so everything's backwards. So this would have to be out, because it's turning it the other way. And then C. I don't even understand why this question's on here, but let's try it out. I thought I'd do something clever here just to check to make sure I'm right. Yes, I'm right. Which one does it spend more time with?
It's the same.
It feels like it should be the same, doesn't it? Because that's going to be a trick question. It's not the same.
B1.
Which one is it?
Isn't it B2?
B2. It takes more time with B2 because it's going the same speed. The speed doesn't change as it's going through these, right? So it's going farther, so therefore B2 is there. It spends more time doing. I have no idea why that question's on there. It's like a super trick question. I'm ready for the trick question. I better check to see what the frequency is over here. Yeah, no, I get the same answer. And yeah, it's just same speed, longer distance, farther, a lot more time. Okay, try number 9s. 9, it's, well, I've got a loop like this. I got current going this way, right? I've got a magnetic field. Which way is it? Into the board. So I've got current going this way, magnetic field this way. Which way is the force for this part of the wire?
Oh, this is still
This way. This way. Maybe more this way. It's not asking what the magnetic force field it's making is. It's saying what's the force on the wire. It caused by this magnetic field. This is the first one, right? So I got current traveling through a wire, magnetic field into the board to the left. That's A. Then number 2. Whoop, whoop, whoop. Current this way.
Ow.
The magnetic force is different at different points, right?
Yes. More perpendicular you are, the stronger it is, right? Because the current's the same, so it's only the perpendicularness that matters. So the net force in this one would be up. Y, positive Y direction would be better phrased. Because these two cancel out. Got a question or a thought, or you curling your hair?
This is me right-handing the thing.
Okay, good.
I mean, I'm on 7, so it's working.
There should just be a little jig. It's like 3 things.
There are, they exist.
Just line it up.
They totally exist. Totally exist. If you get a geeky enough page, they actually do a right-hand roll. They got a right-hand roll little thing. I even seen a right-hand roll that's a top. You spin it and it works. And I'm like, I don't even understand how it works. But okay, whatever. Right? Right-hand roll the way around. Now we go to the right. This one goes left, down, up, right. Now, next question is a little trickier than that. It says, rank wires 1 through 4 from strongest to weakest. That's going to take some thinking. What's going to affect whether it's strong or weak?
Perpendicularness.
Yes. And whether or not they're counteracting each other, right? This force is fighting that force, where this force is not being resisted, right? So these two counteract, right? This one does not. These two counteract, this one does not. But these are equivalent situations right through the same circle. Semicircle. So these two have the same force. And these two have the same force, right? Because they're equivalent. And then, which one's stronger? 1 and 2 or 3 and 4? Tell me why.
there's no counteracting force.
No counteracting forces. It's all pushing the same way. This little bit here would be equivalent to this force over here for 3. All the force on 3.
So what are they all the same?
So these two are stronger than these two. Yeah.
And 1 and 2.
1 and 2 are stronger than the same, right?
And
Because
3 and 4.
they're equivalent. 3 and 4 are the same. Again, the two straight lengths are canceling out.
Yeah.
The curved length is the same. All right, you should be able to do the next part of that. I'm going to skip ahead because I want you to do it for homework if you haven't done it already. So, what other problems do we need to do? 1E. Did we try 1E or did we just say, it's vacation? Couldn't do the first problem, so we didn't do it?
1E?
I'd have to pack it.
Oh, on the back?
Yeah.
Oh, shoot.
Did we do it? Or did we change anything? You create voltage. So what do I mean by change anything? Well, first of all, it has to be a loop. It's not a loop, it's a wire. And a wire, if you run current one way, you change magnetic fields on both sides simultaneously, right? That's not resisting change because you're just changing one side to the other side in preference to the other side, so it makes no difference. So it has to be a loop, okay? And it wants the magnetic field inside of that loop to be the same. So the way we write change is we write ddt, okay? And then we write, what do we not want to change? We're on 14.6.
Yeah.
We don't want to change.
What does the magnetic field not want to change? Number one thing it doesn't want to change is the magnetic field itself inside, right? It does not want that to change. You cannot change that.
Wait, why is it just a lone B?
What?
Why is it a lone B?
Because the derivative of
Oh.
B is the first thing. Now, the second thing's a little strange. It might not make sense to you initially if you think about it, but the area of the loop can't be changed. Okay? If you shrink down the area of the loop, you're changing the magnetic field that's currently protected inside of there, right? And so A can't be changed. And then last but not least is, remember, forces are dependent on direction, right? So you cannot change the angle. And I'm going to tack this in as a cosine theta. Now this item here, to be consistent with what Faraday used to think, even though I don't know if he ever even mentioned this, but people now associate this with him, is called magnetic flux. If you change the magnetic flux, the number of magnetic lines traveling through a loop, the current, they will create a current in the loop which will put it back. That'll resist that change.
So flux is in flux lines as in...
Flux is the flux lines from way back when, those lines going around.
Yeah.
If you change the number of flux lines going through this loop, the loop will respond by creating a current to put magnetic field back into the loop, back in the middle of the loop. Or if it's going up, it'll actually make magnetic field that makes it fight that change. Any change will create this. The direction of the current is whatever resists the change, right? So if current going one way resists the change, that's the direction the current's actually going to flow. The amount of current's dependent on the voltage, as in V equals IR. And the resistance of the wire. Fair enough? Okay, so the way you make potential is what? You change the magnetic field. Change the magnetic field going through a loop, that changes the current, or it creates potential. If you change the direction of the magnetic field, or the loop, either one, turn a loop inside a magnetic field, you're going to create current.
Wait, is the area of the loop one of those?
Area is another thing. If I could figure out a way to change the area. Now that should seem odd to you because we're talking about the area of a metal loop, right? How does that change? I'll show you how that changes.
Like how much you wrap it.
What?
Not how much you wrap it, but how tightly you wrap it.
Right, but but we're talking about actually changing it while the problem's going on, right? We're talking about so for example, I'll give you an example right away. Take a look at the second picture in 14.7 on the bottom right. Or bottom left, either one. No, not the top one, but the next two down below. See the magnetic bar sliding on wires. Okay? So if that magnetic bar starts to move down up and down the wires, it's changing, therefore it'll make current to resist that change. It'll also, by the way, resist the actual bar moving.
That's how we make trolleys.
What do you think on that? My first answer is no, but now that I think about it, that might not be. Most trolleys are electric though.
Yeah, it's the power from above.
Yeah. So most of them aren't magnetic. Well, the magnetic motor is that way, right? You run current, it causes the thing to turn the magnet's torque.
Is this how Elon Musk's new super travel thing works?
Super travel.
Yeah,
Hyperloop.
Remember he bought the Boring Company.
Yes. I imagine those are going to be more like super trains, which is just the maglev is just to get it off the ground, make it frictionless. So basically two opposing magnets sort of thing.
Do we use this for anything cool?
Yeah, power, electricity, if we like it.
Yeah, but it's a slide a bar.
Slide a bar, same thing. You
Isn't
can
that
actually
a-
do it.
Gauss gun?
Gauss gun would work that way too. Is just the change of force. So yeah, no, there's a lot of things that this could play into. There are. Let's explain what it is a little better, and then you can play with that. Okay, so got it? See the idea, basic idea. Okay, so flipping this over, you have problem number 1 on the back to do. By the way, if I have a loop, if I have multiple loops, what would that cause to happen?
Multiple loops.
Multiple loops.
Oh, well,
This is just more.
Multiply, you get more potential. All right, try that out.